Okay, so let's get started, everyone, please. We're just going to now think about boiling points and functional groups. So when we talked about the weak dispersion forces, we were looking at molecules, comparing molecules that have the same length, but they didn't have a functional group. They were hydrocarbons, essentially. Well, oftentimes we're asked to do comparisons between molecules that have this same length of carbon chain, but they've got different functional groups. So maybe something like, let's go with 4. Neater. And we don't even really need to worry too much about naming, but if you can name them, then that's a good thing. What's our first one here? Yeah, it's an alcohol. What kind of alcohol is it? Butane. 1-ol. And what kind of, oh, I know what I haven't given you a, what's this one? What kind of molecule is this one?
Is it a ketone?
It's a ketone. Yep. So it's got the carbonyl functional group, C double bond O, and it's not at the end, so that means it's a ketone. And what's its name? We don't actually need a number. Why don't we need a number?
Because it doesn't matter if it's in position 2 or 3, it's the same.
It's the same. It can't be on the end. If it's on the end, it's no longer a ketone. So therefore it has to be in the middle, and it doesn't matter which way I've drawn it because I can just rotate the molecule and it's around the other way. So this one's name is butanone. What about the next one, while I try and get this attached properly this time? What's our next molecule? It's a carboxylic acid, yep. And what's its name? Butanoic acid. Now, I'm not going to ask you to name this one, but I want you to identify the functional groups. So how many functional groups have we got on this? 2. Yep. What are they?
Hydroxyl.
The hydroxyl, and basically, well, we've got the carbonyl and hydroxyl off the same carbon, and so what we have here is just the acid. So this is an alcohol functional group, and this is an acid functional group. And then this one that I squashed in over here, what's this one? It's an aldehyde, yep. And what's its name? It's going to be butanal, Why don't I need a number? Yeah, it won't be an aldehyde unless it's on the end. And so we don't need a number because we already know it's on the end. We only need the number if there's something else where it could be, another location where that could be. Okay, so we've been able to identify some of our structures here. And now when we're thinking about boiling points, I've deliberately picked examples that all have 4 carbons in the chain. But we're going to be able to rank them as far as boiling points are concerned. Which ones, well, if we look at them to start with, none of them are just going to have weak dispersion forces because they all have functional groups. So what we're looking for are dipole-dipole bonding and hydrogen bonding. Now, we're not going to be able to, the way I've filled up the board already, I'm not going to be able to show the dipole-dipole or hydrogen bonding because I've only got room there for one molecule. To have dipole-dipole bonding, I need to have those dipoles on adjacent molecules attracted to each other because that's what increases the boiling point. We have to add more energy to separate the molecules. It's not breaking any of the bonds within the molecule. Okay, so, but let's just look to see where are those sites where the dipole exists and where are the sites where we've got hydrogen bonding. So in our first molecule, our butanol, what have we got? What can we have? We can have hydrogen bonding. Why can we have hydrogen bonding?
Doesn't that involve hydrogen and oxygen?
Yeah, for hydrogen bonding between molecules, we have to have the hydrogen attached to either an oxygen or a nitrogen molecule. If it happened to be a nitrogen, is it going to be stronger or weaker hydrogen bonding than if we were attached to the oxygen? So if we look at our periodic table here, and if we know that fluorine is the most electronegative element on the periodic table, it's the best attractor of electrons. And the trend is across towards this way. So we're increasing in electronegativity across the periodic table towards fluorine and up the periodic table towards fluorine. And so when we're ranking oxygen and nitrogen, it's going to be which one is closer to fluorine is going to be more electronegative. So the oxygen is more electronegative than the nitrogen, and so if we have hydrogen bonding present on an oxygen, we're going to have a higher boiling point than if we had a comparable molecule that had hydrogen bonding onto a nitrogen. Okay? And so you can see here that there's going to be a greater difference in electronegativity between the carbon and an oxygen than there is between a carbon and a nitrogen. All right, so we have hydrogen bonding. How many sites on the molecule? 1. What about for our ketone? Yeah, we've got a dipole. How many? 1. Then we've got the carboxylic acid. What have we got there?
Dipole, dipole, and hydrogen.
Yeah, yep. So we've got a dipole. Here we have the dipole. And we've also got hydrogen bonding. One of each. Now just remember that this is not the dipole-dipole bonding yet, because I've just identified the dipole, I haven't drawn the bonds between molecules. What about on this one here? What have we got? Yeah, so this time we've got hydrogen bonding, 2 sites, and dipole, 1 site. So yeah, this one here is going to be the hydrogen bonding, and this one here is a dipole. And then lastly, we've got the butanol over here. What kind of?
Dipole.
Yeah, so we've got a dipole. How many? 1. So we know that hydrogen bonding is the strongest of the weak intermolecular forces. So things that only have a dipole are going to be the weakest of the attractions and have the lower boiling points. That's going to be our aldehyde and ketone in comparison to our other 3. Now, geometry also comes into it, and if we've got our dipole on the end of the molecule, it's going to make it easier to interact with adjacent molecules. So we would see a slightly higher boiling point for the aldehyde than the ketone. Does that make sense? So if here we're comparing, basically they're almost identical, aren't they? The difference is geometry. And so then we apply the logic from geometry. Which one's easiest to collide together? Then we're going to rank these 3 that have the hydrogen bonding present. Which one will be the weakest? Sorry? I can't really hear. The butanol? Yeah, so this one's going to be the weakest. Why?
Because it's only got 1 type?
Yeah, so it's only got that one kind of attractive force between other molecules. This one's got that and something else. And then what about this one? This will be the highest, won't it? Yep, because it's got 2 sites for hydrogen bonding as well as a dipole. So that's the kind of thing that we're looking at when we're trying to rank molecules as far as boiling points are concerned.
So if we had a molecule, would we ever come across a molecule that had like 2 dipole on the end?
Well, you could. You could have 2 dipoles. In fact, just say, if I have this one, and I could have something like this. That's going to be a dipole as well.
Yeah. So would 2 dipole on the end be greater than just 1 hydrogen bonding on the end?
Now that's where it gets a little bit tricky. Yeah. So to be able to figure that out, I think a question might have the boiling points, and then you'd have to explain why you see what you see. Yeah. Because that's going to be hard to explain which way you've ranked it and why. Yeah, so I think, yeah, but you could definitely have a table of boiling points, and then you'd be explaining what are the factors that are influencing those boiling points. Okay, any other questions about ranking? Okay.